this lecture, we are going to revise week 0 and week 1 solutions, so that I want to complete this playlist so that it will help us in the exam that is NPTEL going to take for this course VLSI Design Flow RTL to GDS. So let's follow on with the solutions of the week 0. So the first question is about which of the following values can a binary bit or digit can take. So binary digit means 0 and 1, so it's very clear. Second question, binary equivalent decimal number 8 is, yeah, it's 1000. How do I get to know what is the decimal equivalent of 8? It's very easy. It's you follow the you know this code 8421 code, and it is based on the value that number takes in terms of binary, the weighted value. So the first digit will be 2 raised to the power 0, second will be having weight of 2 raised to the power 1, next will be 2 raised to the power 3, and subsequently 2 raised to the power 4, 2 raised to the power 2 raised to power 2, and then 2 raised to the power 3. It started from 2 raised to the power 0. So 2 raised to the power 3 is 8 only, so it is 1000, right? Very easy. The decimal equivalent of binary number 1010 is 8. The weight here is 8, here is 2, 8 plus 2 is 10. The sum of two binary numbers 1011 and 0011 is 1 plus 1 will become 0. I will get carry as 1. 1 plus 1 will become 1, and carry will be 1, and 1 will come here, and 1. Yeah, 1110 is the output. Logically AND. So yeah, this one is AND. When both input are high, output is high. Rest other case, output is 0. Next is XOR operation. XOR means if exclusively any of the input is 1, then only output is 1 in case of two inputs, and rest other case both are 0, output is 0, both are 1, output is 0. A 2:1 multiplexer selects the input based on the select line value. Select is 0, I0 is selected, select is 1, I1 is selected. Which of the following statement correctly describes a flip-flop? The flip-flop are edge triggered by a clock. Which of the following statement correctly describes a latch? So when a enable signal of a latch is inactive, a latch retains its old value. When an enable signal of enable signal of a latch is inactive, a latch loses its old value. When the enable signal of a latch is inactive, a latch is always produced a 0. When enable signal of a latch is inactive, the latch is always produced a 1. So general notion of latch is that I am not giving any signal, like when my latch is inactive, it should hold its older value. Okay. So when the enable signal of latch is inactive, it retains the old value. This one is the correct option. The CMOS inverter consists of, yeah, CMOS inverter, very basic. It consists of one P channel MOSFET and one N channel MOSFET, that we call it as PMOS and NMOS. PMOS is connected to VDD, and then PMOS and NMOS are connected, and the NMOS then NMOS source is connected to ground, and PMOS source is connected to VDD. So it's very basic. This one is correct. Okay, let's see here also. All answers are correct as well. Fine. Let's move to week 1. Week 1 assignment questions. We'll have a look. I did 2 mistakes here. So, okay, we will correct our mistakes also. That's the point of revision. So, the first one is, which of the following statement is correct regarding a die fabrication in a silicon wafer? So, let me give you a brief introduction. How does it happen? Like when we do this photolithography, so photolithography is a process of fabricating the various layers in our IC, in our integrated circuit. So what happen is that we have a die area. I will go to the slide, then it will be more clear. Let's go to the slide where from there this question is taken. I think in tutorial materials. In tutorial materials lecture 1 only. Yes, I hope it is visible. So here if you see, photolithography has come. what happen is that we put a seed of silicon, very pure silicon, in the molten silicon, and we take out the silicon ingots, and from the silicon ingots we carve out the die. We carve out the die. Die is basically a silicon wafer containing, means the silicon wafer is there, and we make 100 of rectangular shaped integrated circuits. We make uh, this is square shapes, and from in these shape we are going to carve out our circuit which we want to make. And then when each of these when each of these rectangular region or the square region is being when carved out of the die, like when carved out from this wafer, I'm sorry for that, if you carve out from the this wafer, then that is called a die. And when the die is when packaged properly, encapsulated and given the pins and all, then that is called as a chip. A chip can be placed in the chip holder, like suppose the your laptop has motherboard, so that is also a motherboard has some chip. Motherboard has a chip, so that chip is placed in the motherboard. So that is one of the example, like the mobiles also have the chips. So chips have the pins and all, it is properly packed, and that is placed in the PCB basically. So that is the chip. So what is the flow? Let's understand it properly again. So we put molten silicon we have a molten silicon, and we place one very pure seed of silicon in that, and we when we take out that seed, we get silicon ingots, and we carve out and this silicon ingot is very pure, and then we carve out from this silicon ingot the wafers, and in wafer we make this rectangular region or this square region, and in that region we fabricate, right? We fabricate based on the description schema that we obtain from the design companies like NVIDIA. We got the design, and based on that design we have this GDS file. GDS file is basically a detailed layout description file, and based on that layout we are going to uh, print our various layers and make our IC. So that small region in that wafer is going to call die, and hundreds of die, which means 100 of chips are basically going to get ready in that wafer. And when we carve out and we take out when those dies, and when we fabricate them properly, when we encapsulate them and give it a protective give the protection, and then they are called as chips. Chips are now ready to get placed in some PCB to make the system work. So that's how basically the flow will go. So now if we come to that question, that was week one question, which I did wrong at that time, but we are going to correct the mistake here. So we perform photolithography for creating transistor on die before slicing. No, that is not correct. Basically, in that die area, there are various sorry, in that wafer there are numerous number of dies, hundreds and hundreds of dies. So in each of the die, in hundreds and hundreds of die, we are going to fabricate our transistor logic, and then we are going to carve it out. So we perform photolithography for creating transistor on die after slicing that die from the wafer. This is not the correct one. So we perform photolithography for creating transistor on die before slicing that die from the wafer. Yeah, this is the one. A is the correct option. Anyway, answer is also now visible. So let's see why this is correct now and why others are incorrect now. So B is incorrect. Now go to C. We create metallic connection between transistor on die before slicing that die out of the wafer. Yes, the metallic connection to the transistor, that is that we have studied actually, since we have now at the end we have already completed this course. So if you know, in the later part of the course we have studied that the metallic connection that we give, right? Metallic connection that we give to do the to connect the various devices layer through the interconnect layer. So they are actually metallic connection only. That only is metallic connection. So that we give to die before slicing it out. That is correct. And then because this is the way to fabricate the various device layers and they interact with each other through that metallic connection, then I say that my chip is then I say that my chip is ready. Then I take it out. I mean, then we take that die out from the wafer and do the further processing to make it a chip. So yeah, C option is correct, and the D1 is incorrect. So it was asking that before, but it was saying that it is after slicing, but before slicing is correct. Second question I is which of the following statement is true? So I didn't mistake that I put this one like fabless design companies make PDK to foundries for fabrication. So it's a two-way process. It is a circular process, I would say. Uh, if you go again to, I guess it was there in lecture number 2, I guess. Is it in lecture number 1? No. It's lecture number 3. In lecture number 2, we go, we will find that. Lecture 3, if I go, mm, let's, okay, there was one diagram which which told how the PDKs, I mean, how the design companies and the fabrication companies, how are they interrelated? For some reason, I'm not able to find that right now. Please, where is that? I think it is in week one itself. Let's go to week one. This one is the week one. Mm, yeah, this one. So the design team makes some design and they give that design to foundry. The physical design layout, the properly detailed layout description they give to foundry, and the foundry have will produce the chip and foundry, the requirement of the foundry is there in the kind of chip that we that is needed and the standard cells that is needed to make that chip, and those are there in the PDK file, the process development kit. It contains various standard cells and libraries through which we are going to make our design. So the question here was saying that fabless design company provides PDK to foundries, but it is not correct. It is the foundry that gives their process development kit or PDK to design team, and design team based on this PDK, based on the libraries, based on the cells, we are going to do our design and give our design to foundry for the fabrication and make the chip. So it is the foundry that give PDK to design team. It's not the other way around. So therefore, this option is wrong. And NVIDIA is a fabless design company. That is correct. Fabless design means they don't do fabrication. They do only the design thing. That is the fabless term mean. So this companies like Qualcomm, NVIDIA, it's written in the slide also. Let me show you. Yeah, companies like Qualcomm and India, they do not require a setup to maintain the foundries, because setting up foundry and keep it running is a very costly task. So there are some companies who are totally dedicated for the designing of the chip. Like giving the idea for the RTL code, from gaining the idea from the RTL code, optimizing the RTL code, to coming up with the proper detailed layout and the optimized layout with detailed routing and all, and then finally taping it out and giving it to the foundry. So that completely the designing part, and the fabric design companies do the only designing from RTL to GDS, only designing. So RTL to GDS is completely related to designing part. So the designer, we can work on any of this, from the front end, which comprises of RTL coding, to the back end, which comprises of this physical designing and all. So NVIDIA is a fabless. This is a correct option. Rest other option, let's go and revise all these questions as well. Third one is, which statement best describes the features of FPGA based design? So FPGA main motive is to give us flexibility. By flexibility means FPGA consists of hardware, but that hardware can be programmed using software. That is the idea. So it gives us a sort of flexibility, and from that we can, if my requirement is low number of IC, like if suppose I say only 10 IC. So in that case, I will not go to foundry, and then I will say that okay, give me 10 IC for, like, fabricate 10 ICs for me, fiber design also. So it is better to, if my requirement is low, like I requirement is low means I want a low number. I mean the amount of ICs I want is less in number. In that case, I would go for FPGA based design. So FPGA design means the design effort will be minimal with just from software coding. The one Vivado, Xilinx, if you know, is a platform from which we can actually program our FPGA. So these kind of things, if we program our FPGA using some software, so it will require a design effort to be minimal, right? So based on the software coding only, my hardware will align in such a way so that my intended function is delivered. And the performance power area definitely will be inferior compared to the cases when we have a completely optimized layout that we do in full custom layout based system, in uh, and in standard cell based system. So compared to them, definitely the performance power and area related terms that we call as figure of merit, that will be inferior. But the fixed and it has a lower fixed cost, definitely, because there is a greatly design effort is reduced, and when the design effort is reduced, so the fixed cost is going to get reduced. So from where I got all this reference here, if you see, mm, FPGA based design. Okay, this is from lecture number 2. Yes, there are 4 kind of design. This one. So there are programming blocks in FPGA based design, and programmable logic blocks, and they will form the interconnection as per our requirement. And the PPA, the performance power and area, is comparatively inferior, and design task is minimum. And there is no mask layout. I mean, what you program, you get that IC itself in FPGA. That is the great advantage. The flexibility of FPGA makes it a go-to tool for our daily simple hardware-based modeling. Okay. And if you are going into a specialized kind of thing, if you want to make some application specific IC, then full custom design and standard cell-based design are preferred. These two are preferred. Now let's again go to this. And so these all are correct. So all of them are correct. Fourth one, among the following statement, which statement correctly describes the abstraction of RTL? So what does it mean by RTL, Upodi, huh? So RTL contains data flow description typically written in hardware description language, that is Verilog and HDL. RTL consists of algorithm typically written in C++. No. Verilog is somewhat similar to C, but it is not actually C. C is a procedural language, but hardware is a language different. In hardware, what we are saying that how are my wires are going to get laid, how are my which will go input to my logic gates and all. So it doesn't follow this procedural format that a C language follow. And like suppose it will run in sequential manner C program, but In HDL language there is not an issue, because HDL means we are visualizing a hardware itself. So that's why it is different from C. The way of writing is somewhat similar to C. RTL consists transistor level description typically written in SPICE, not correct at all. RTL consists of layout and GDS format. No, no, no. So this only option is correct. Right. It is written in Verilog and VHDL. Next question. We need to select the true statement. So we use same mask for all the metal layers. No, no, no. Every layer of the every layer of my IC, they have different mask, because the interconnection that is going to happen with the device layer, that is going to different. That will be different. So we have a different mask for different layer, and there are 10 to 15 layers in a typical IC. So we have the same mask for all layer. That is not a correct statement. A is incorrect statement. B option. Design description at a higher abstraction level contains more details than description at the lower abstraction detail. So at higher abstraction, what we have, higher abstraction mean our details are hidden, right? Higher when abstraction increases, the level of detailing decreases, and vice versa. So when we are at the RTL stage, then we have a higher abstraction, and design description at higher abstraction level contains more detail. So that is incorrect, right? So if we are at higher level of abstraction, it means we have a greater flexibility to optimize my circuit, but actually we don't have very much detailing about the thing that we are going to create. As we go down further in the process, from RTL to RTL coding to the physical designing, and from physical designing to uh, routing, and then the taping of the IC. So in that way we go to the more detailed way. Therefore, design description at higher level contains more detail is incorrect, and description at lower. So actually at lower abstraction level, my detail will be higher. So B is also incorrect statement. C1 is full custom design, cell based design, and FPGA based design of the example of design cell. Definitely. Full custom design, cell based design, FPGA based design, and there was another called as gate array based design. So these all are few design styles. So C is the correct one, right? Which of the following statement is correct regarding behavioral synthesis or high level synthesis? When you do the high level synthesis, it means that we are converting an untimed algorithm which is written in high level algorithm to an RTL code. Uh, High level language is used to write that algorithm, and it is converted to the RTL model. RTL means register transfer level. So that is the way which can be further broken down into various logic gates and netlists through which our functionality is going to be achieved. Therefore, the B statement is correct here. It converts the untimed algorithm written in high level language into RTL model. Like in the RTL model also, you are only going to give the clock signal. So these all are detailed. These all are given in my RTL code, the Verilog code itself, and from there we give this information, and we convert that algorithm into high level language, written in high level language. Sorry, the algorithm is written in high level language. Some high level language is converted to RTL code. Seventh one is, which of the following can be the cost matrix for behavioral synthesis? So area, latency, power dissipation of the ghost, all of the above. Yes, performance, power, and area. Performance is related to power dissipation. Performance related to latency, like how fast my circuit is. Power is this one, and area is, yeah. So all of the above is correct. Which are the advantages of designing a chip at higher level of abstraction such as RTL compared to directly making a layout of a transistor? So if you are directly going to make a layout, then what will happen is that it might not be optimized. What I am trying to say here is that when you are at higher level of abstraction, we have great detail of making the optimization part. We have great flexibility of making the twisting the thing in such a way we are going to an optimal solution. So that is the idea. Making changes and exploring trade-off can take less time and computational effort in RTL. That is correct. In RTL we are just coding, so if you do some mistake in coding, you can quickly fix that code, right? But if you do in the designing part and in the layout part, if you do any mistake, then the reverting that thing will be more tedious. Therefore A option is correct, and the B option is timing analysis is more accurate at the RTL compared to layout. So timing analysis is more accurate is RTL is incorrect, because at RTL level we don't know how the actual circuit is going to behave. Like we don't know the various factors like the parasitic capacitances, for example, the resistance between the wires. These things are not clear at all when at the RTL level. So timing analysis is very less accurate at the RTL level. And the C option is it is more accurate to compute parasitic capacitance RTL. No, that is not correct. And at the physical design level, when we are when we do this parasitic extraction, and then it is accurate to compute this parasitic extraction. C is also incorrect, so only A is correct. Ninth one, you have to match the following. What is a layout? Layout is optimally design logic gates and make available in library. Yeah, this is a standard cell. Standard cells are optimally designed logic gates. So B4. B is connected to 4. A logic cell is optimally designed logic gates and they are available in library, and we can make the chip based on the library files, and the logic gates are already optimized. Then what is layout? Okay, layout is final design representation of GDS format provided by the design team to the foundry for fabrication. Yes, that is actually correct. The layout is the layout that we give to the foundry is the GDS file. That is the graphical description of my chip. It contains the detailed layout information itself. So with the help of detailed layout in the foundry, what will happen is that uh, with that layout, my mask will be created and photolithography will be done, and various layers of the chip are going to be made. So in this way, an IC will be fabricated. Therefore, a layout is a final description. Actually, it would be more accurate if I have written GDS. It would have been written GDS, but okay, layout is this one. Second is standard cells. So it is optimally designed logic gate. What is IP assembly? IP assembly is uh, a kind of a sub block, if you say. Like suppose uh, there are various logic gates are required to make some complex combinational circuit or sequential circuit. Let's say I'm designing some complex multiplexers. Let's say example, I'm making a multiplexer. It contains various logic gates. So that logic gate can be considered as an IP assembly. IP means intellectual property assembly, or the macros or the blocks that we say. So instantiating various pre-designed and pre-verified subsystem on blocks and SOC for making their connection. Yeah, that is IP. That is IP. If we go in physical level, here also we first place the IP, the larger blocks, the macros in our die area. Then we place the standard cells, right, in the placement stage. Therefore, the IP assembly means the C is connected to 1, and the RTL design means higher level of abstraction of design consists of functionality at the register transfer level. Very much clear. So yeah, this one is the correct. The 10th one is what is the advantage of employing behavioral synthesis in a design flow? So what is the idea of giving behavioral description? It allows automatic exploration of different possible RTL at the same algorithm. Yes. What happens in behavioral synthesis? A different possible RTL like gate level RTL, or for example this behavior level RTL. So we actually do this exploration is possible at the same for the same algorithm. This is the one advantage of employing behavioral synthesis of RTL. It always increases design effort on a chip. No, not at all. It's just a code, and we can tweak around the code and get our required functionality. It generate RTL often lacks readability and debuggability. Not no not a correct statement. because we can have a good readability and debuggability, because it is just a code, right? Therefore this option is not correct. So the third one was saying we have the exploration of different possible RTLs for the same algorithm. Yeah, for the same algorithm we can come with different RTL, different possible RTL codes to achieve our required functionality. So this is correct. So that's all about this week 0 and week 1 assignments. So thank you. Next we'll come with the further week assignment solution. In this way we are going to revise and let's give our best for the exam.